Hello and welcome to the next chapter in our nuclear fusion odyssey here on Physical Attraction. This episode is called Pinches, Stellarators and Perhapsatrons. So last time we talked about the first time that humans were able to create fusion in the lab, the process that fuels the stars, in the course of making weapons. We discussed Edward Teller's fanatical obsession with a super bomb, and then him stealing the credit from Ulam for actually designing it. After concerns with fallout from some of the nuclear tests led to the Test Ban Treaty, Teller continued to draw up plans to use nuclear weapons in a bizarre program known as Operation Plowshare throughout the 1950s and 1960s. The stated aim was to use hydrogen bombs to carry out civil engineering projects like digging canals, because I guess conventional digging is just way more boring than nuclear-assisted digging. But in reality it was probably to allow weapons development to go ahead, to continue to justify large research and development budgets, and to test nuclear weapons in a way that was plausibly not about warfare in violation of the Test Ban treaties. Now, Teller's views were far from typical amongst scientists. We've described in many of our episodes about nuclear weapons how these early physicists faced a particular dilemma. At the time it was a unique dilemma. These days, though, it's ever more common. Those who research CRISPR gene editing or artificial intelligence or geoengineering or nanotechnology will understand this dilemma. The technology you're looking into is dual use. It has the potential to do great good, but also to do great harm. What's more, the way you look into it, the decisions you make, the possibilities that your research might open up, and the potential for unintended consequences, can influence whether or not this technology is used for good or ill. Imagine those nuclear physicists who had seen their breakthroughs become the cold mathematics behind the devastation of Hiroshima and Nagasaki, and now plunge the world into a thermonuclear standoff. They have no doubt that understanding the secrets of nuclei could unlock tremendous, world-changing forces, and they are desperate to show that stealing this fire from the gods is justified. That the human species can harness these powers for good. That, rather than the first step along the road towards our self-destruction, splitting the atom can help humanity towards an enlightened world, a scientific, rational world, a world where nuclear power provides immense benefit for the whole species. Of course, this is difficult because, technically speaking, even in the Sun, nuclear fusion is, in a sense, impossible. The Sun's plasma consists of nuclei and electrons that have been separated. The nuclei are fully ionised by the immense heat. We've already described in previous episodes how you need to supply nuclei with an immense amount of energy to overcome the so-called Coulomb barrier, the electrostatic repulsion between the protons in the nuclei. As any pair of nuclei approach each other, they rapidly decelerate as their kinetic energy is converted into electrostatic potential energy due to the charges being forced closer together. So you need to get your nuclei to have an immense amount of kinetic energy before they can dream of getting close enough, on the order of femtometers, for the strong nuclear force to take over and fuse them together. This would then release energy which can heat the plasma further. Now, if the rate of fusion is fast enough for a self-sustaining reaction, the plasma will ignite and burn at a steady temperature, which you can usefully extract heat from, with the energy released by the plasma partly going into the heat that you extract, and partly going into helping more nuclei to fuse. So this is the dream of a nuclear fusion reactor, replicating the same process that powers the Sun here on Earth. But in the Sun, it's strictly speaking not possible. At least not possible with classical mechanics. Even with the immense heat and pressure in the heart of the Sun, where temperatures regularly get up to 15 million degrees Kelvin, the kinetic energy of the protons is simply not enough to overcome that Coulomb barrier. You can do simple calculations, e.g. with the widgets on Hyperphysics Online, that tell you that the approximate temperature required for the average nucleus to have enough energy to overcome that Coulomb barrier just through thermal energy, just through the energy it has from being in a hot place, is 4.6 billion Kelvin. Now, even the heart of our Sun is 300 times colder than it would need to be for your average nucleus to be able to fuse under those temperatures. The weirdness that allows for our Sun to burn, and hence for the universe as we know it to exist, is of course quantum weirdness. You may have heard of quantum tunneling. We'll get into it more in future episodes. But this essential idea is that the precise position, energy, momentum of particles, etc. has a certain degree of uncertainty to it. In fact, it doesn't make sense to say that a subatomic particle is in a particular location, that it has a particular energy, or that it exists with a particular momentum. You can't pin it down with a precise set of coordinates. Instead, the most complete description you could hope to give is a probability distribution over space. The particle has, say, a 10% chance of being in this range of positions, a 20% chance of being over here, and so on. Instead of a particle, which we imagine as a small point-like object at a very specific coordinate, you have a wave function of probabilities, places that the particle could be. It turns out that this means that particles have a finite probability of turning up in regions where they'd be classically forbidden to tread. The same thing happens with alpha decay. You might remember from our radiation episodes or the episode on Rutherford's gold foil experiment that the alpha particles escape from a nucleus. Well, classically they couldn't actually do that, they don't have enough energy. But those alpha particles have some small probability of being sufficiently far outside the nucleus to escape. And that's precisely how those decays work. This phenomenon, where particles appear to tunnel through energy barriers that should be impossible for them to escape from, is quantum tunneling. And quantum tunneling effectively lowers the energy barrier and allows fusion to occur in stars like our Sun. So when you're considering the immense challenge of making fusion work in laboratories on Earth, bear in mind that it's only the strangeness of quantum mechanics that allows the damn thing to work in stars. First, you need some ability to heat plasma to temperatures comparable to that at the heart of the Sun. Then you need some way to hold that plasma at immense temperatures and pressures, sufficient to ignite a self-sustaining fusion reaction, without the whole thing exploding. These are not easy challenges. Very roughly speaking, what you're looking for is something that can satisfy the Lawson criterion for a self-sustaining reaction. This is sometimes called the Lawson triple product and has been rewritten and estimated for many different types of approach to fusion. It was first declassified in 1957, as the focus began to shift from achieving high temperatures to confining those hot and dense plasmas for a sufficient time for a self-sustaining fusion reaction to arise. The triple product is the temperature of the plasma, multiplied by the density of the plasma, multiplied by the approximate lifetime of its confinement. That confinement time is set by how quickly the plasma loses energy due to radiation and mass loss from the plasma. To achieve a self-sustaining reaction, you need a very dense, very hot plasma to be confined for a significant amount of time. You can make the plasma cooler, but then you need it to be denser so that it radiates less energy away, so that it has a smaller surface area to radiate energy away for every particle you have. So decreasing any one of these, density, temperature, or confinement time, must come at the expense of increasing the other two. Yet when you make matter extremely hot and dense, the result is an enormous amount of pressure on the walls of your container. The temperature is also intolerable. The element with the highest boiling point is tungsten, a frankly pathetic 6,000 Kelvin or so. Diamonds can't even get you that high. For a start, if you heat them in air, they burn and emit carbon dioxide. If there's no oxygen supply, first they turn into graphite, a more stable allotrope of carbon, and then they sublimate, that is, the solid burns straight away into a gas, at around 4,000 Kelvin. When physicists first started to calculate the possibilities of deuterium fusion, they thought that the temperatures that might be required for a self-sustaining reaction on Earth could be as high as 500 million Kelvin. In other words, no substance on Earth could possibly contain a plasma that hot without swiftly being vaporized. So if plasma were held in any known container on Earth, the confinement time would be far too small to be useful, and any small amount of energy you could produce from fusion would just end up being used in vaporizing the container. Now you could go down the Edward Teller route of using atomic bombs to explosively compress deuterium fuel. This is the similar principle to the way that the fusion bomb works. You use a normal atomic bomb to provide that compression that you need. But hydrogen bombs were not the peaceful source of energy of the future. As George Thomson, a British physicist who will become crucial to this part of the story, wrote, quote, "One answer would be to make the confinement time very small by using extremely high densities, but such a device would be the same as a hydrogen bomb, and we are not interested." End quote. It's difficult to pin down the earliest origins of this idea, but at least by 1946 physicists were experimenting with what seemed to be the only reasonable solution, confining the plasma using magnetic fields. Sufficiently strong magnetic fields can of course levitate charged particles. In fact, Ed Geim, who won the Nobel Prize for discovering graphene, famously also won the Ig Nobel Prize for using a particularly strong magnetic field to levitate a frog via the diamagnetism of the water in its cells. But if you had such a magnetic bottle that was holding the plasma in place, your plasma needn't touch anything, and therefore there's no issue in finding a container that can hold it. The laws of electromagnetism, Maxwell's equations, were already known and quite well understood at this time. The Lorentz force law, for example, tells us how magnetic fields act on charged particles. Charged particles actually only feel a force from the magnetic fields when they move through them. When a charged particle moves through a magnetic field, a force acts on it that's perpendicular to its velocity and to the magnetic field itself. If your magnetic fields are aligned just right, you can hope to confine the plasma for long enough to get a reaction going, without needing something the size of the Sun. This is the field of magnetic confinement fusion. So imagine you have a magnetic field pointing into a piece of paper, through the plane of the paper. Then imagine that you have a charged particle moving parallel along the piece of paper, say from the bottom of the paper to the top. The Lorentz force will then tend to deflect it to the left or right, depending which way your magnetic field is pointing. Because the force is always perpendicular to the velocity, this is essentially precisely the condition for circular motion. In just the same way as the Sun, constantly tugging on the Earth perpendicular to its velocity, drags it into a roughly circular orbit, so you can use the Lorentz force to confine charged particles in roughly circular orbits around the axis. This is of course similar to the techniques used at particle accelerators like the Large Hadron Collider, and we can deduce things like the temperature of interstellar gas and dust based on how they rotate through the background magnetic field of the galaxy. In a similar way to how charges moving through a magnetic field generates a force on those charges, moving charges themselves generate a magnetic field that's perpendicular to their motion. For this reason, a coil of wire, sometimes called a solenoid, generates a magnetic field that goes straight through the heart of the coil when you pass a current through that coil. So you have a current that's going in loops around the axis, and it generates a magnetic field along that axis. Again, this is very well understood. Rotating coils of wire in magnetic fields to produce electricity is the basis for pretty much all electrical power generation, aside from solar energy, and would be for a nuclear fusion reactor too. The only difference is where you get the heat from. So if you wrap a coil of wire around a tube and pass a current through it, you should produce a magnetic field that will go along the axis of the tube. You can then imagine plasma spiralling in a tight little helix around that central axis. This is the natural motion for particles in a magnetic field. Imagine injecting charged particles into a magnetic field. Now in the direction perpendicular to the field, they'll be pushed into circles that orbit the magnetic field direction. Parallel to the magnetic field, that is in the direction it goes, no force acts on them, and so they just carry on moving. The result is a sort of corkscrew helix motion around and along the axis of the magnetic field. So if you imagine particles on their natural orbit in this magnetic field, sort of rotating around the field and moving along it gently with their drift velocity, you have a pretty good idea of how they behave. Less than a mile away from where I typed this, in Oxford University's Clarendon laboratory, some of the earliest magnetic bottles for fusion plasma were designed and tested, as early as 1946. British physicists were amongst the first to come up with a design for a magnetic bottle, based on a concept called the pinch effect. The idea here is to start with a cylinder of plasma. Remember that plasma is just a hot mixture of electrons and nuclei, a bit like a gas but fully ionized. Because the plasma is full of charged nuclei and charged electrons, it's made of charge carriers, and you can seek to pass a current through this tube of plasma in a similar way as you would a wire. When you pass a current through the tube of plasma, though, the result is a magnetic field perpendicular to that current. It tends to force the plasma inwards, crushing that cylinder onto its axis. Fans of high voltage electricity will sometimes use a similar effect, the crushing inwards force of the magnetic field, to crush aluminium cans. You can even see it in the effects of lightning strikes on lightning rods. The sudden shock of the vast current compresses and pinches the lightning rod, bending it out of shape. So there's this force that pushes towards the axis based on this current flowing, based on the magnetic fields. The idea with a pinch fusion reactor is to use this force to compress and contain the plasma. As an added bonus, the compression of the plasma makes it denser and heats it up, alongside confining it. You can imagine that perhaps, if you pump a sufficiently high current through the plasma, the pinch effect might just be enough to cause a self-sustaining fusion reaction in the centre of the reactor. This idea, and variants of it, passing current through the plasma to squeeze and compress it into a fusion-ready state, were the very first designs for fusion reactors. The first patented fusion reactor was in 1946 by British physicists Thomson and Blackman, and based on this design. Of course, one issue with a tube like this is that the plasma isn't confined at the ends and spills out. One solution you might come up with, of course, is to make sure that there is no end. You have a torus, a donut-shaped tube, surrounded by a coil of wire. You can then force the plasma into a circular orbit and confine it for a longer time without spilling out of the ends. But there is an issue with the simple toroidal design, a donut shape. A donut, if you imagine, has an inner and outer ring. Clearly the radius of the inner ring is smaller than the outer ring, regardless of how you build your donut. If you imagine wrapping a coil of wire again and again around the edges of a donut, you'll quickly realise that on the outside of the donut, where there's a bigger radius, the loops of wire will be spaced further apart than they are on the inside of the donut. This means then that your magnetic field isn't perfectly symmetrical, is it? It's actually stronger towards the centre of the donut, where the loops of wire are closer together, as they're only spread across the small inner radius of the donut. The nice, ideal, even magnetic field you had before is ruined. Now you have a field gradient, which forces the electrons and nuclei in opposite directions, and before long, your ordinary torus has nuclei and electrons drifting out from the walls of the container. You might think, oh well, we could just make the outer and inner radiuses really close together. But if you do that, well then there's actually less potential for that sort of lateral movement along the axis if you think about it. You have to come and try and strike a balance between how bad this drift problem is and how much space you give them to drift. Because if you make the donut very, very thin, then there really cannot be any major field gradient, or you will just have stuff drifting out straight away. And of course there's a limit to how small the donut can be to contain the plasma, the magnets and all the other apparatus. Fermi pointed out that eventually, for reasons of pure geometry, this arrangement can't work. The plasma will eventually separate and escape. The torus then leaks from its sides, and you can't get good confinement just with this method. There's a famous story that Lyman Spitzer, who would go on to be the founder of one of the earliest laboratories solely dedicated to nuclear fusion in the United States, hit upon what he thought might just be a solution while he was riding a ski lift. He was an avid mountaineer, and he'd just received a phone call about a blockbuster New York Times story on nuclear fusion, one that we'll cover in our next episode, relating to the activities of a certain Ronald Richter. Perhaps there is something to be said for an era before gadgets allowed us to be occupied at all times, and a situation like being stuck on a ski lift meant that you were forced to keep yourself entertained. The story goes that Spitzer, who just happened to be a very clever astrophysicist who studied the plasma that is the interstellar medium surrounding us in our galaxy, came up with a new design. This would be based on a figure 8 design, with two donuts connected together. The idea here is pretty simple. If you imagine the plasma travelling through the figure 8, you can see that it will pass through one of the loops clockwise and one of the loops anti-clockwise. This is important because the Lorentz force that acts on these charged particles is very concerned about whether they're travelling clockwise or anti-clockwise. Now, you still have this drift towards the edge of the tube, but it's in opposite directions in each half of the tube. Therefore, if you construct your figure 8 just right, or so Spitzer hoped, the drift will cancel out, and you'll have decent enough confinement to make a working fusion reactor that doesn't leak out of the sides. Now he assumed that the predominant way that energy would be lost from the plasma would be due to Bremsstrahlung, so-called braking radiation. When charged particles accelerate or decelerate, they emit radiation. This is how matter and light interact, and why, for example, we can generate radio waves by moving these charged particles around. The electrons in the plasma are charged particles, and they'll collide with nuclei and other charged particles. They're accelerating and decelerating, thus releasing radiation and losing energy. And similarly, as they rotate around the axis of the figure 8, they are accelerating all the time, because anything that rotates is accelerating in towards the centre of that rotation. That's how it changes direction, because acceleration can be a change of direction as well as a change of speed. So the electrons in the plasma will always be radiating away this energy and losing this energy. Now if you assume that this is how plasma loses most of its energy, you can get to a figure of around 50 million degrees Kelvin. That's the temperature at which you break even. The fusion reactions you're producing generate enough energy to cancel out the losses due to radiation. But this was still 5 times hotter than any temperature that had ever been achieved in the lab at this time. To produce reasonable power, you'd probably need at least 100 million Kelvin, and a way of confining that plasma. But Spitzer was still optimistic. He got a grant in 1951 and began work on this new fusion reactor, giving it the grandiose title of the Stellarator. Compare this rather fancy title with the name that physicist James Tuck named his devices, constructed to exploit the pinch effect at Los Alamos. He was a veteran of both the Manhattan Project and the early experiments with magnetic confinement fusion, and in 1951 he also managed to get funding to build his reactor based on the pinch effect. Tuck was sceptical of Spitzer's optimism. He felt that, quote, a self-sustaining thermonuclear reaction should not be thought of until, at least at first, we've created a detectable reaction, and then we've worked out the problems of ionization, conduction, and the effects of magnetic fields on a small scale. End quote. He was concerned that in a large, spatially spread out plasma, thermal conduction would take too much energy from the plasma, like in the Stellarator, and hence the pinch, which involved the fusion occurring in a much thinner filament, was a more attractive prospect. Spitzer felt that his device was better. It worked steadily, constantly, while the pinch device worked only in pulses, which Spitzer felt would eventually prove impractical for generating power. Tuck and Spitzer met in May, discussed their designs, and both came away feeling that they were still right. So fusion in those early days was already a camp divided. Tuck, slightly less confident in success, called the pinch device he was working on the Perhapsatron. Tuck, who had perhaps been amongst those physicists dazzled and horrified by the Trinity atomic bomb test years before, would spend the rest of his life pursuing fusion in some form or another. Alongside this, there was a design that was tentatively called the magnetic mirror, which would confine the plasma to a tube by kinking and curving the magnetic field at its cap. If the magnetic fields were made stronger at the ends of the tube and weaker towards the middle, then it might serve to reflect the plasma, bouncing it back and forth in the tube so that it can be confined for long enough to cause a sustainable fusion reaction. The late 1940s and early 1950s must have been an incredibly exciting time for nuclear fusion. Just think about the historical context that these scientists were dealing with. Just 30 or 40 years before, no one alive knew that there was even such a thing as a nucleus. In just 11 years then, people had gone from having no idea that nuclear chain reactions could possibly exist, to ending the most devastating war in history with 2 of them. Nuclear physics was a field where ideas were going from inconceivable to impossible to works in progress to prototypes to world-changing deployment, all in the span of 10 years. And now, in 1951, physicists were a year away from finishing a bomb that used nuclear fusion, and had 3 potentially competing designs that were hoping to use magnetic confinement fusion to become the energy source of the future. In Spitzer's initial research proposal for the Stellarator, he suggested that it might provide 150 megawatts of power. That would put it on a par with some conventional power plants. Yet you wouldn't depend on fossil fuels. Nuclear fusion reactors also have a large advantage over nuclear fission reactors in that they are sort of fail-safe. A nuclear fission reactor is more or less a controlled explosion. Your chain reaction is moderated by the type of fuel that you put into the device, or the control rods that are raised and lowered to change the rate of the reaction. As the people at Chernobyl found out, if you fail in your efforts to control that chain reaction, the results are always explosive. But in magnetic confinement fusion, if your efforts to control the plasma fail, what happens? Well, the plasma might crash into and melt the walls of your reactor, and probably destroy the reactor itself. That's going to cost you an awful lot of money, and is obviously a bad thing, but it won't be anywhere near as bad as an accidental meltdown at a fission reactor can be. The very worst scenario is that some of the tritium gas produced leaks into the surrounding environment, and you have to shut down the site and move somewhere else for a few decades, if the secondary containment vessel for this gas also fails. But it's nothing like Chernobyl, or any other disaster. There's no potential for a catastrophic explosion which could spread radioactive material a long way away. Fusion technology alone also can't be used to create a nuclear bomb. You would struggle to weaponize magnetic confinement fusion, although we'll talk about issues about nuclear waste and so on in a future episode. But it seemed at the time that this would be a new source of energy that could be shared with the world, without worrying about whether countries that claimed to want atoms for peace were really interested in atoms for war. Already in the early 1950s, though, we were seeing this hyperbole about how fusion would soon power the world and move us into a new nuclear age, energy too cheap to meter, unlocking the boundless potential of the sun. Can we really judge people too harshly for getting overexcited about the potential for the new technology? There are entire religions based around this now. So next time we'll talk about the first fake fusion detour from progress, Ronald Richter's Argentinian Gambit. As nuclear fusion grows in the public consciousness as a solution to so many problems, the temptation to make somewhat premature claims about having discovered it also grows. This is just the first example, but it actually wound up being historically important, even though it was a very obvious hoax at the end of the day, because it sparked a lot of the funding into fusion research that happened later. In fact, it was this very story of this scam that Spitzer was thinking about when he sat on his ski lift and came up with the Stellarator. So never let it be said that fraudsters and failed experiments can't change history, just not in the way that they might have hoped. Then, once we've dealt with that little detour, we'll deal with the early designs of Stellarators, pinch fusion reactions, and magnetic bottles, and the 1958 experiment in Britain that led a national newspaper to print a banner headline across their front page that said, "A son of our own, and it's made in Britain." I'll see you then. Thanks for listening to this episode of Physical Attraction. You can contact us at www.physicspodcast.com. The contact form goes to email, and I always read that. There's Twitter @PhysicsPod. There's Facebook, Physical Attraction. And there's all manner of other ways you can get in touch with us too. If you have any comments, questions or concerns, the contact form on the website is probably the best. Also on the website you'll be able to subscribe to our Patreon, where you can download the bonus episodes in exchange for a small donation, or you can donate to us on PayPal and buy the bonus episodes that way. Anything you give us is much appreciated and helps us keep the show going. But of course the best thing you can do to help keep the show going is review us somewhere visible, tell your friends to listen to the show, and generally spread the word if you've enjoyed it. Until next time then, take care.